Okay. Well, this book here, when I get to the STAHL section, it talks about two organisms. The first one talks about, in general, is the finger and toe organism, and then the second organism it talks about being like the mycorrhizae as a separate unit sort of thing, which is then goes into the oh yeah, that's much better. Much better. Must be my eyesight going. I'm getting old, fellas. I'm 55. So, yeah. The soil had become acid to litmus paper where the lime had not been used. It is interesting to note that though barley would not grow, oats flourished freely on this sour soil. There are, however, two special organisms which merit further consideration. The fungus, which clothes the finer rootlets of many classes of plants, forming mycorrhiza, should be mycorrhiza, I think, and the slime fungus or plasmodiophora, which causes the disease known as finger and toe or club root, I suppose, as we call it now, in turnips and other cruciferous plants. The term mycorrhiza is applied to the symbiotic combination of the filaments of certain fungi, which complete development has not in all cases been observed. Well, there you go. And the finest rootlets of certain plants. Sometimes the fungus forms a sort of cap to the exterior of the rootlets, which are generally without root hairs. Well, there you go, without root hairs, and we talk about the DIONAEA having long persistent root hairs. So, in other cases, it penetrates the cortical tissue of the root itself, which may also be furnished with root hairs. There you go. According to researchers of Frank, the fungus of the mycorrhiza lives in symbiosis with the higher plant, attacking the humus. There you go, humus is important then, and also the mineral resources of the soil. So you need both minerals and humus to help make the plant grow properly, I would say. Blah blah blah, and passing on the food thus obtained to the host plant. In some few cases, the host plant possesses no green assimilating leaves and is wholly dependent upon mycorrhiza to obtain its necessary carbon from the humus. Such a case is seen in the Neotia, Nidacavus or bird's nest orchid, to be found chiefly among the beech underwoods in this country. In other words, leaf mould. There's probably a connection there with slack 1, and then he goes into slack 2 and it totally goes away from leaf mould for cephalosis or something in his second book. Did he sell out, or did he just go slack? Joke there. More generally, the host plant is capable of nutrition in the ordinary way when growing in the media in which the nutrient salts are abundant. Oh, there you go. When the nutrient salts are abundant, they don't need the fungus, but becomes microtrophic in soils and situations unfavourable to the production of directly absorbable food. Okay, you know, things like bark chips, I would say. Something like that, I would say. As for example, in heaths and moors, where the soil is almost wholly humus, or beneath the shade of trees, where nitrates are rarely found, and where illumination is insignificant for such assimilation. Later researches, particularly those of STAHL, STAHL, have shown that the symbiosis of mycorrhiza, instead of being a phenomenon restricted to a few species, is widely diffused among many classes of plants. Because now we know, it's 97% plus of the families of plants in the world are mycorrhiza. So why not carnivorous plants, you see? There's that other argument. By their own definition and research, you would expect the mustard aren't, because they actively put chemicals into the soil to retard and repress these sort of things. Yeah, so they can actually get access to the nutrients themselves by keeping the fungus from robbing the nutrients and sending off to other plants sort of thing, in a way. And you can also use them to actually semi-fumigate or sterilise the soil in a way, sort of thing, using mustard seed and things like that. But so then again, why aren't CPs there, Yeah. Do they produce chemicals a bit like mustard? Well, wouldn't they stink or something like that? You know, see, there you go. When's the last time you dug a fly trap out of a pot and it smelled got there like garlic or something like that? You know. Yeah, you see. There's no empirical a priori evidence there, you know, in your face sort of thing, you know. Anyway, let's carry on. Adapted to expose a large... here we go. It has already been indicated that the cultivated plants give off considerable quantities of water by transpiration. Therefore, you can see they need to be in bogs because they transpire a lot, you know, if they are mycorrhizal. The form and arrangement of their leaves are adapted to expose a large evaporating surface. The root is well developed and provided with root hairs. So there's the connection, root hairs. We do know they have long persistent root hairs, but are the roots well developed in the wild? Well, what about Darwin being sent the banana that was 80 centimetres tall? And it has a, yes, I've been sent a root. Didn't he say in the thing, I've been sent a root? I can't remember if he actually mentioned how long the root was. But that would be interesting too. And I've seen one of these plants of that sort of stature sent to someone in a lump of soil from the southeast, from some lady in the southeast. That's all bloke would say. I think we all know who the lady is, but you know. It used to be in our Mycological Plant Society and moved down there. So, provided with root hairs to keep up the supply of water to the plant. There are, however, a number of plants in which transpiration is much less active. So we've all got to keep a humid environment, swampy soils. The leaf area is restricted to otherwise arranged, diminished loss of water, so that the proportion previously stated in existing between the dry matter produced and the water passing through the plant is greatly diminished. A diminished supply of water to the root would, however, necessitate a loss of nutriment to the plant, as nutrient materials to some extent must enter the plant with the transpiration water. Ah, well that seems very interesting, isn't it? They have to go in the xylem rather than, yeah. That is interesting, yes. STAHL has shown that in general these plants with a small transpiration activity are furnished with mycorrhiza, by means of which they obtain food of all kinds. From the soil, all kinds, so it's not just the minerals then. So he's almost subtly implying they can also get the sugars as well. That would be very interesting when they do get the sugars. That's probably why you need the humus, because you know, newspapers say it's basically long chains of sugars, basically. Long moiety chains of sugars. So you break down your cellulose, you've got your sugars, your various sugars, depending on what type of cellulose it is and whether they've got alpha, beta or gamma bonds, of course. We know that you know, cotton wool has the gamma bond and therefore it's resistant to degradation when it's saturated beyond, I think it's 80%, I can't remember now what it is. And it's also resistant to seawater. So there you go. So saline soils. My dad did a lot of PhD research into degradation of wood in seawater and things like that. So I got the hand-me-down, not like you got a hand-me-down of cardigans, I got the hand-me-downs of all his papers, and I went through them and picked out the really interesting ones. So the one about the cotton wool was very interesting. I learned about the gamma bond and everything. So. Anyway, keep going here. Another interesting generalisation has also been brought into line with the above facts by observations of STAHL that the microtrophic plants with a feeble transpiration do not store starch in their leaves, but contain instead considerable quantities of soluble carbohydrates, chiefly glucose. Now glucose is a reducible, it reacts with copper and it will reduce copper basically. Yeah. So it's a reducing sugar, so it will reduce copper. So maybe the plants can actually tolerate copper if they reduce it. Hint, hint. Okay. In normal plants, though, sugar is the first tangible result of assimilation. It is rapidly removed from the sphere of action by being converted into starch. Such withdrawal of the product of the reaction being necessary if a rapid rate of assimilation is to be maintained. Should, however, the sugar accumulate in the cells, the concentration of the cell sap is increased. In other words, they're sort of implying this sort of seesaw balance between, of osmolarity between sugars and salts, basically. I think that's what they're getting to. Though many exceptions can be observed, there seems to be a very general association of the development of microwaves with a diminished transpiration in the absence of starch from the leaf, and especially among plants such as orchids, lilies, irises, or there's a lot of that sort of stuff in WA, kangaroo paws and the like sort of thing, which often grow in dry or shady situations, such plants being further distinguishable by a shiny, glossy leaf surface. STAHL has again shown that the average proportion of ash to dry matter in the leaf is lower for microtrophic than for normal plants. So less ash, so if you burn the leaves, there's bugger all there, basically, what he's saying. It's basically water and sugar, basically. Yeah. Little starch. Whatever the nutrient may be present with the mycelia of the fungi, everywhere transfers humus in its natural state. By direct experiment, it has been shown that normal plants growing in humus develop better when the humus is previously sterilised by long exposure to chloroform vapour than when it is in fresh condition, for the living mycelia competing successfully for the nutriment. The absence in the leaf of calcium oxalate, well, that is strange, because rhubarb, we know, has oxalic acid in its leaves. And nitrates, in particular, characteristic of microtrophic plants. Okay, so I don't quite get which way he's saying that with the nitrates. The absence in the leaf of calcium oxalate and of nitrates, so there's no nitrate, is particularly characteristic of microtrophic. So they don't have nitrates in the leaves and they don't have oxalic acid, so so where does rhubarb fit then? That's a hole in our theory, isn't it? Unless you can actually make them, you can actually switch them on and switch them off, sort of thing. They are adaptable, they have an alterable metabolism or something like that. We'll find out. They do have some very strange pits or pores on the at the end of the before the leaf and the petiole, a bit like you've got some strange pores on like plum trees and things like that. If you go back from the the fruit and the leaf, you will see some brightly coloured little almost like they're attractive to ants and things like that. So maybe there's a connection there between rhubarb and plum trees and things like that, and maybe alder, the classic one, the classic David Bond tree, alder, is that how you say it? Yeah, the man who reinvented I can't remember now. It's gone out of my head. Anyway, the other type of plants, the aerobic ones, the ones like with casuarina, Aussie pines and casuarinas, where they have the breathable nodules, not the anaerobic nodules of legumes, but we have actually aerobic breathable nodules. Because it's not a bacterium, it's a pseudo-fungus sort of thing. Because all fungus are supposed to be aerobic organisms, you see. Strictly aerobic, they say, but when they say when you're investigating an unknown quantity, you always have to keep that in the back of your mind, that they probably haven't discovered everything in the world and they haven't got everything down pat yet. So there might be something new out there, basically, or something straddling the fence, the best of both worlds, or something like that. Anyway, STAHL concluded that symbiosis between the roots and the plants and the mycelial fungus is a very general phenomenon, especially characteristic of plants growing in soils subject to drought, or poor in mineral nutrients, or rich in humus. So there's the three basic groupings where you'll find these sort of plants. So I suppose low in mineral salts if you talk about sandy soils. These microtrophic plants are generally of slow growth, possess a feeble transpiration and limited root development. Their leaves rarely contain starch. They are also characterized by containing a comparatively small proportion of mineral salts, among which calcium oxalate and nitrate are notably absent. Two of the mycorrhiza associated with these plants are the genus Erica. The power of fixing atmospheric nitrogen has been attributed, but the question still requires further investigation. Now that comes through the work of Meredith Rayner, of course, with her work with vaccinium and the like sort of thing. She actually showed that the fungus can go up through the plant and infect these seeds in the actual ovule, basically. That's what she came to the conclusion. I have all of her papers except one. So, yeah, and I've read them all, as you can tell. Showing that the mycorrhizal fungus is carried in the seed coat, there we go, and is essential to germination, and that's her work. He's basically connecting her work to his work, basically. I've actually got that paper. I'm missing the Cocker paper. Have you got the Cocker paper? I'm missing that one, you know, the DIONAEA Cocker paper. It's a very short paper apparently, but it has a nice map, they say, so I know. Has this thing run out yet? Let's see. But we've got another thing, maybe want to... It's very interesting. Blah blah blah. Rich in humus, blah blah blah, 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 blah. Oh, here we go. Sometimes absent on the roots. The plants growing in dry, sandy soils, poor in humus. The existence of... no, how do you say the word microtrophy? With certain interesting applications in practice, blah 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 blah. Typical in gardens. Examples are orchids, ericas, lilies, and other general plants which must be grown in leaf mould, peat, or other materials rich in humus. There you go, leaf mould and peat. So that's probably why he started talking about leaf mould after peat. He's probably read this book as well. Yet, yeah, I'm not talking slack, of course. Other materials, though equally rich in humus and possessing similar mechanical properties, prove quite unsuitable. Now that's an interesting point, isn't it? Other materials with similar properties and mechanical properties, other materials, though equally rich in humus, with similar mechanical properties, prove quite unsuitable. Now that is really an interesting point when you think about it. So the search for a peat substitute is going to be extremely difficult. I found that to be quite true. Okay. It is easy to surmise that this effect, confined in the main to microtrophic plants and humic soils, may easily be due to the absence of the proper fungus from the soil found to be unsuitable. So he's saying that maybe the point is hard to find an alternative to peat is you've also got to have the organism there. So, but as I said, I think we've got a generic one from my research anyway, and evidence I've put up online. It has also been shown that the difficulty usually experienced in raising seedlings or exotic orchids which die off in great numbers just because they don't have large extents, the mixing with the medium with the seed, blah blah blah, and that's the bloke with the bee, and because he discovered he could replace the whole bloody organism by just having sugar there. I think if I remember rightly, Bernard, I've forgotten his name now, but yeah, that's what he basically started the tissue culture craze for germinating orchids seed, basically. You know, forget the fungus, just give them a bit of bloody sugar in the thing, and you can get them to germinate in a flask, a sterile flask, of course. So yeah, and then when they get big enough, you can actually inoculate them, sort of thing. But you can get them growing to quite large size, and then you can just transfer them to a pot that has the organism in it. I think it's run out now, isn't it? So anyway, I think we've done most of that. There's probably, if there's any other really important salient points in the next and just one more large paragraph, but if I find anything in there, I'll put it on another one. But I think we've got to, we must have got to the end of this one by now, surely. I've probably missed all the important information. But, oh no, we're still going, so you got all that, so, anyway. So you got your Drossa gigantea on one side, you got your large 80 centimetre Drossa banana with long roots as well on the other hand. That was on this thing. You could talk about the concept of climax. You know, you can't just stick them in any old soil. It's again a bit related to this book. You've got to actually have the soil develop, and also the landscapes have got to develop that way. You go from one ecotype to another. It's complex concept. You can run the concept in basically two separate ways. Graham Bond plants, Meritus rainbow, and there. God particle or wanker particle. I'm going to talk about that.